Hello, my name is Charles Wade. I'm a PhD student at the University of Colorado Boulder. Today I'm going to be continuing my series on using OpenVCAD to design various multi-material objects. Today we're going to be showing and talking about some examples of designing soft robotic actuators with OpenVCAD. So to get started, we're going to look at one of the most powerful things that OpenVCAD can provide to designing soft robotic actuators, and that's periodic functions, right? So here we have this actuator, or rather a cross-section of an actuator. This would normally continue all the way around, and we're just looking at a slice through it. Now, what we've done here is we've defined the geometry with this function node. So this function uses periodic, sine functions to actually define our geometry. It's a function of x and y, which means it'll extend kind of forever in the vertical or the z direction. And as such, like I talked about in my mug example, the constructive solid geometry example video, I bound that, or take the intersection with a bounding box to make sure that doesn't extend forever. We actually do define a stopping point. And then we apply this functional grade, and that's the extra special thing I want to talk about here today. So notice how we have this function right here. If we actually look at this function up here, it's basically the same thing, we just have a different coefficient on it, right? So we're tweaking this coefficient right here to actually modify the gradient geometry, or the material gradients in the inside of this geometry, right? And notice how I'm using the threshold mode here. So threshold is going to say whenever or whatever material is dominant in that region is whatever material it should be. If I change this to probability and we re-render, you're going to see, So one of the things to notice here is the threshold mode. So I'm using the threshold mode here to create a hard material transition between these two boundaries without defining any separate geometry. So I'm not using any kind of unioning or Boolean operations. This is purely a material definition in a single region of geometry, right? Allowing us to define both a red and blue material. Now, what's something we can do with this is, since this is the same function we use down here with a different coefficient on the front, we can use it to create kind of different channel sizes. So right now we're using kind of 3.5, which makes for a good channel size. We could envision this red material perhaps as representing our, our air channel that's going to be going through here, and the blue material soft, and it's going to inflate and bend the actuator. But we can kind of change it. So if we make it 4.5 in re-render, you can see that got a lot smaller, right? Just by changing it a little bit. If we go to 5.5 here and render, you can see it gets kind of smaller. We get this zigzag effect on it. And then if we go to 8.5, you can see we get what's almost like a cylinder straight through it. So just by changing, these two coefficients on the front of these distributions, we can actually dramatically change what's going on inside of this object. So I'm going to turn it back to 3.5 so we get a good channel size, and show you one other thing that we can do. So I've taken it back. We've got this red material, but let's say this does represent a fluid channel in the center to actuate this. We can actually use a special keyword here that's defined in all VCAD material definitions called void. Right? A void material is just that. It's no material. It's the absence of material. So if we go ahead and render this, you can see now we've hollowed this out, right? So without using any kind of geometric means to do this, we can actually just do this with material definitions as well. In the case of this, with hard material transitions, or hard material boundaries, we can use it to hollow. You can also use the void material to erode designs. So if you want things to be intentionally porous, you can use functional grading with a material and a void to create things that have programmable porosity. So another actuator that I will show you uses functional grading again. So if we go ahead and render this one, right, this is that same design we were looking at before. I've gone ahead and stopped taking a cross-section through it. I'll show you what the cross-section looks like in a second, but right now it looks pretty much the same. We can see there's a little bit of red mixed in here. We might not be sure what's exactly going on here. If we look at the top, well, now we see there's a gradient, right? Okay, we're grading in some kind of red core to it. Now, if we want to actually, peer into what's doing it, the ray trace preview gives us a good opportunity to do that. Unfortunately, if you're using just the traditional voxel preview and you don't have a GPU, you're probably just going to have to take a cross-section through this to be able to see it, which I'll show you in a second. But since we are in the ray trace preview, we can peel back the blue, and oh, there's that red core. Yeah, we can see there's this kind of porous red core that's mixing in with blue, to form this kind of gradient effect. Let's say we do want to take a cross-section through. All we need to do is just sample this and stop short on one of the axes. So I could set this to 0. I can render with ray tracing again. Now we can see a cross-section of what's going on through here. If we zoom in, you can see we have some transparency, and we're kind of viewing at that mixing core. This also works for rendering the voxels the traditional way without the GPU, and we can visualize. So the final example that I want to show is this other soft robotic actuator. So we're going to go ahead and render this. Oh, not this one, my bad. This one. So if we render this one, we're going to see quite a bit of stuff going on here. So let's go ahead and move the light to see this a little better. So you can see we have lots of hard material transition boundaries mixed in here, right? So these represent certain regions that are stiffer than others that actually create this compliant mechanism. So when inflated, we've got cyan, blue, yellow. These will be assigned different material channels in the printer and actually represent different mechanical behavior. So this is all controlled using this fairly complicated function that defines the materials, and then a separate but similar function that defines the actual geometry. It should be noted, much like the examples I've shown in the past, this one also uses cylindrical coordinates. So you can see rho, phi c, that is to differentiate from phi s, right? Phi c is phi cylindrical, phi s is phi spherical. We can actually mix and match cylindrical, spherical, Cartesian coordinates all in the same VCAD design and all in the same functions. They'll all be evaluated and converted automatically when the tree is sampled. So this is just a method to allow us to differentiate these two. Important thing to know.